So let's now go through an example to demonstrate a race condition. Now we could easily have both threads count down to 1 without skipping numbers by not passing the same countdown object to both threads. So instead, what we're going to do is create two countdown objects and pass one to thread 1 and the other to thread 2. Because of course at the moment, as you can see on lines 8 and 10, we're passing the same object. So by doing it this way, by creating an object for each and passing a different one to each of our threads, both objects are stored in the heap and are shared, but since thread 1 would only work on countdown object 1 and thread 2 on countdown object 2, there wouldn't be any interference. So let's change the code just to demonstrate that now. So we're going to change it. We're going to use countdown 1 here. And let's also create a second one, countdown 2. And then we're going to pass countdown 1 to thread 1 and countdown 2 to thread 2. So let's run that and see what happens. I'll run it a few times just to confirm. What you should be seeing here is that there's no interference. We're still getting objects running, or the results rather, printed out in a different order, and that's because the operating system is suspending the threads and starting them again. But what you can see here is now there's no interference. So we've got each thread is successfully counting down from 10 to 1. But unfortunately, this solution often won't work in real-world applications. So as an example, imagine if the objects represented here were bank accounts or employee records. We can't provide each thread with a different object. It wouldn't make sense to do that. So every time a bank manager or employee file is accessed and changed, we have to use the same object to maintain the integrity of the data. Otherwise, how do we know what the bank balance should be after several threads have changed it? So in the case of bank accounts, there could be several threads waiting to change the bank balance at the same time. There could be a thread making an automated deposit, perhaps a thread making a scheduled bill payment, and the owner of the account doing some online banking. So in order to ensure the integrity of the bank balance value, we need to allow multiple threads to change it, but we also need to prevent a race condition, which is thread interference, which we talked about and went through in the previous video. Now, fortunately, Java provides us with a way to control when a thread can change a value in the heap. The process of controlling when threads execute code and therefore when they can access the heap is called synchronization. So we can synchronize methods and statements. Now, when a method is synchronized, only one thread can execute that at a time. So when a thread is executing the method, all other threads that want to call the method or any other synchronized method in that class will suspend until the thread running the method exits it. Then another thread can run a synchronized method, then another, etc. To be clear, if a class has 3 synchronized methods, then only one of these methods can ever run at a time and only on one thread. Now, since only one thread can execute a synchronized method at a time, threads can't interleave when running a synchronized method. So what that does is it prevents thread interference within synchronized methods, but not outside of those methods. So if the same instance variables referenced within a synchronized method are also referenced outside it, in code that multiple threads can run, and that particular code isn't synchronized, then we may still see thread interference. When working with threads, we have to synchronize all areas where we think or where interference can happen. So let's change our example back now to only using one countdown object, since we've established that a real-world application couldn't have separate objects as such. It wouldn't work. So I'm just going to undo those changes. And just to confirm, we'll run it. We should see that the threads are now skipping numbers again. So we are getting that interference again. So to synchronize a method, all we really have to do is add the synchronized keyword to a method declaration. So seeing as though the work is being done in the do countdown method, we just need to change this by adding synchronized, like so. Now when we run it, you can see that thread 1 counts down without skipping any numbers, and then thread 2 does the same. And notice when I run it again, we're getting the same results every time I run this. And that's because this synchronized, by adding the synchronized keyword, we're now saying that we want this whole method to run, before another thread gets access to it. And that's why you can see thread 1 finishes in the entire thread, the entire method, and then thread 2 gets its chance to do the same. So in this scenario, they're never going to interleave because only one of them can execute the do countdown method at a time. Now, unfortunately, we can't synchronize constructors, and if you think about it, it wouldn't really make sense if we could do that. Only one thread can construct an instance, and until the constructor has finished executing, the instance won't be available for other threads to use anyway. But what we can do is synchronize any other method. So that's one way to prevent a race condition. The second way we can do that, we can prevent a race condition, is to synchronize a block of statements rather than an entire method. So every Java object has what's called an intrinsic lock, and we'll also see this referenced to as a monitor. So we can synchronize a block of statements that work with an object by forcing threads to acquire the object's lock before they execute the statement block. Now, only one thread can hold the lock at a time, so other threads that want the lock will be suspended until the running thread releases it. Then one and only one of the waiting threads can get the lock and continue executing. So looking at our code in the do countdown method, the only code we really have to synchronize is the for loop. Thread interference doesn't affect the rest of the code since we're setting a color based on the thread name. So what object will we use to synchronize the for loop? We can't use the counter variable I because it's a primitive type, not an object, and primitive types don't have intrinsic locks. So at first glance, the first thought might be to use the color object to synchronize the for loop. So let's try that and see what happens. So to synchronize a set of statements, we just put them inside a synchronized block. So let's look at doing that. So I'm going to add some code here to line 36. I'm going to type synchronized, and we're going to use color. And then we're just going to put the for loop within that synchronized block. So let's run that and see what happens. And what we'll do is we'll remove the synchronized keyword from our method now because we no longer want to synchronize the entire method. We're now doing the alternative approach to just synchronizing a block of code. So we'll remove that and run that. And you can see we've got a different result, and clearly there's now some interference again. So why is this happening? Because only one thread can hold the color object lock at a time, so only one thread should be able to execute the for statement. That's in the synchronized block on line 36. The other thread should have to wait until the first thread has finished its countdown. But as you can clearly see by me running this example, we're seeing the same type of results we got when we weren't synchronizing at all. The problem here is that we're using a local variable to synchronize. And you recall that local variables are stored in the thread stack. Each thread will create its own copy of the local variable, and each copy is an object that has its own lock. Thread 1 gets the lock for its copy and continues executing, and thread 2 gets the lock for its copy and it continues executing. When we want to synchronize using an object, we have to use an object that the threads will share so that they're both competing for the same lock. Using local variables as a result won't work. The only exception to this is using a string variable, and the reason for that is string objects are reused within the JVM. So in other words, the JVM uses string pools for allocation of string objects. And I'm only mentioning this now because you may see examples of a local string variable being used to synchronize code, and you'll be wondering why that works. And the synchronized code we've got here using the color local variable doesn't work. So that's really the only exception to the rule. As a general rule, it's easy to just remember not to use local variables to synchronize full stop. Now, before we fix our example, I really should reiterate that when using a local object variable, the object reference is stored in the thread stack, but the object values are stored on the heap. Now, since the threads will each create their own copy of the object, so the object references will then be different, there won't be any interference even though the object values are in the heap. Essentially, the thread stack will only ever contain primitive values and object references And to be fair, function references, but that's really outside the scope of this lecture and not related to race conditions. So let's fix our example. So we've worked out that color doesn't work here because it's a local variable. So it would actually make sense to synchronize using the countdown object that the threads share. So we can do this by synchronizing on this. So let's try it by removing the reference to color and changing that to this. And we try running it. And just run it a few times, and as you can see that at this point the threads no longer interleave or skip numbers. Only one thread can run the for loop at a time. And you can also synchronize static methods, and you can also use static objects. When you do that, the lock that's used is owned by the class object associated with the object's class. So I'm going to finish the video here. In the next video, we'll continue our discussion about synchronization. We'll go into a bit more detail about that. See you in the next video.